Greetings folks, it's Professor Fiore. In today's video, we are going to take a look at the low frequency performance of a common emitter amplifier. So let's pop up our little schematic here. And what we have is a fairly straightforward dual supply little BJT amplifier over here. We have a modest bit of swamping 100 ohm resistor. So I've got as an input a little sine wave, 100 millivolts peak. It's going to drive the bass, and of course we expect to see an appropriate output signal. We can do some quick approximations to figure out what we're expecting. So if we were to use approximation that the base voltage, the DC base voltage, was going to be about 0, compare the size of these resistors. All right, we should be able to do that. Maybe this will be minus 0.1 volts or something, but pretty close to 0. That means this 10 volts is going to drop across the base emitter, so there's about 7/10, and then these two resistors. So you're going to have 10 minus 0.7, 9.3, now maybe a little less because of the drop on the base resistor, 9.2, 9.3, somewhere around there, dropping across a total of 4.6K. That's going to give you about 2 milliamps of current. So the R prime E, 26 millivolts over IE, 26 millivolts over 2 milliamps is going to get you 13 ohms. So our gain would be the RC value, right, the AC value, which is going to be this DC bias resistor of 5K in parallel with the load. So 5K in parallel with 10K is going to give us about 3 1/3 K. And we're going to divide that by the R prime value of 13 ohms plus the swamping of 100, right? So 113 ohms for that. Now that's going to yield a gain of just under 30 in this particular circuit, inverting of course. But what I want to figure out is the effect of these capacitors, right? We've got an output capacitor, an input capacitor, and an emitter bypass capacitor, which by the way, I have started off with some really huge values because I want to put them well below the audio range. And then what we're going to do is we're going to change each one by itself and see what the effect is. How can we calculate the low frequency limit of this amplifier? And it is essentially controlled by these three capacitors. C in and C out create classical lead networks. The bypass capacitor is just a little bit different. You can approximate it as a lead network, but it's not a true lead network. Nonetheless, let's start off with a simple transient analysis on this amplifier with a 1 kilohertz input, just to verify that the break frequencies, the roll-off frequencies created by these capacitors is well below the 1 kilohertz. And then what we're going to do is we're going to use our formula over here, our critical frequency formula, which is just a variation on the capacitive reactance formula, right? Critical frequency is 1 over 2 pi RC. All we've really done here is we're going to sort of equate X sub C and R. At that point, something kind of interesting happens, which I'll explain in just a moment. But in any case, let's go up here, and first we'll do a transient analysis just to make sure that things are working the way we expect. Alrighty, so expand this out so you can see it a little bit better. And oops, wrong button, sorry about that. Put the legend up here. So we've got our input and our output. So we can see the input is in fact pretty small, 100 millivolt. We had a gain of, like I said, a little under 30. That's what we're expecting. So we would expect a little under 3 volts. And in fact, there's our peak, there's 3 volts. So that looks pretty good. I'm pretty happy about that. All right. Now let's go in and we'll do an AC analysis. We'll do the AC transfer characteristic. So I'm going to start this off at 1 hertz and go up to 1 megahertz. Now what we see is a nice flat gain response out here. So here's 1 hertz up to 1 megahertz. One thing I want to point out is that the gain is in decibels. Coincidentally, an ordinary gain of 30 is just about a decibel gain of 30 decibels. We do things in decibels. There are some conveniences to this, which we'll see down the road. But for now, there's really only one thing you have to remember, and that is this scale is only in tenths of a dB. So that's not even really audible. That's a very, very small percentage in terms of a gain change. In fact, 3 decibels, and this is a key thing to remember, 3 decibels represents a doubling or a halving of power. If a signal goes up by 3 decibels, the power associated with it has doubled. If it goes down by 3 decibels, the power has been cut in half. Now, because voltage and power are related through a square, right? Power is equal to voltage squared divided by resistance. To get that factor of 2, you don't need a factor of 2 in voltage. A factor of 2 in voltage, that's 2 squared, which is a factor of 4 in power. So in fact, you only need a square root of 2 for the voltage change. So to see the power cut in half, which is how we define the cut points, the roll-off points for an amplifier, to see that half power point, we're looking for minus 3 decibels. And that will turn into 1 over the square root of 2 times the ordinary voltage. We all know that is approximately 0.707. So we would be looking at about 0.707 of the voltage. That would indicate where we have the half power. All right. Okay, so what I'm seeing over here is a gain that's pretty close to 30 dB. And even down here at 1 hertz, we're only looking at, well, actually less than half a decibel. So that's really, really tiny. So this gain is very nice, all the way down to single digits. Now, what we're going to do is we're going to come in and we're going to start monkeying with these capacitors and see what happens, right? So basically, we've verified that these capacitors are all producing roll-offs at these super low frequencies, all right? Okay, so let's start with the output network. I think this is the easiest one to see. And what we're going to do is simplify this, make an AC model of this little output network here. So we've got the transistor, and we model that as a current source, of course. There is an internal resistance associated with that current source, but for typical values of biasing resistors and so forth, it's high enough to ignore. So what we end up with is a current source, and we have this RC value. The DC power supply will be shorted, essentially, right? Remember your superposition. So for AC, we'll short that. So this RC goes to ground. We have the cap, and then we have the load. So what we wind up with is something that looks like this. Right? There's our current source for the transistor. There's the 5K in parallel with it, the output capacitor, and a load resistor. All right? Now, some people prefer, I happen to be one of them, prefer to look at things in terms of a voltage source rather than a current source. I think it makes seeing voltage divider effects a little easier. So we can just do a source conversion, right? So you have a current source with a parallel. We do a source conversion on that, and we come up with a voltage source with a series resistor, right? So there's your 5K and our source voltage. So it should be apparent just by looking at this, as we go lower and lower in frequency, capacitive reactance gets bigger and bigger and bigger, and consequently we start losing some of this generator signal across the capacitor. It doesn't get to the load. So you can think of this as a frequency-dependent voltage divider, basically. All right. So the question is, where does this really start kicking in? At really high frequencies, if X sub C is only a few ohms, well, you're not really going to see any effect, right? This signal is just going to have a standard divider between the 5K and the 10K. You could think of this as loaded versus unloaded voltage gain, basically. But nonetheless, it's only until the frequency gets low enough that X sub C starts getting into the K-ohm range that we start seeing appreciable loss. So where does that occur? Well, it occurs where X sub C and R are the same size, the effective R for the whole thing. Well, what is the effective R for the whole thing? Well, we would simply do a Theveninization. We would find what's the resistance, the Thevenin resistance that drives C out. Right? So in other words, you'd break open the cap, look into these terminals, and what do you see? right? The voltage source would get shorted. You'd see RC, the 5K, in series with our load, the 10K. So that's 15K ohms, all right? Now, you could prove this to yourself very quickly if you set the X sub C of C out to 15K ohms, so it matches the resistive value. At that point, the voltage you're going to see out here is going to be 0.707 of the total. Don't forget the phase shift caused by the capacitor. So, we don't say it gets 50% of the voltage because of the phasor, because of the phase shift on the cap. We do in fact get 0.707, in other words, 1 over square root of 2 of that. And again, that's the value that'll give us 3 dB. That's the value that'll give us half power. So we can analyze this, we can calculate this. I've changed the capacitance value to 100 nanofarads because, I want to isolate this network from the other two networks. I don't want to have all three networks, fiddling around at the same time. I want to isolate it so I can see the effect of just one. So here's 100 nanofarads, and as I said, we have a total of 15 k ohm. Let's go back to our original circuit, right? So I changed this 100 micro to 100 nano, nice factor of 1,000, and there's our two resistors. We plug it in here, right? So R is 15K, C is going to be 100 nano, and we see what we get. Well, that calculates out to a little over 100 hertz. It's about 106 hertz. That's where we should start to see this thing roll off. In other words, the 3 dB down or half power point at the low frequency. So let's just go in and do a little Bode plot here, an AC analysis, and see what we have. Oops, guess what I forgot to do? I forgot to change this capacitor. All right, dumb teacher, bad teacher. Okay, yeah. Let me see my capacitance here. 100 nanofarads. All right, that's better. Try that again. Alrighty, so again, here's the 30-ish dB that we had last time. Let me just get a cursor on here. You can see what our readout is. Bring this over here. All right, so we can see that we are in fact getting about 28.8 on the y-axis. That's our decibel, and of course the frequency up front. So at 28.8, I'm looking for 3 dB down, or about 25.8. Where does that occur? Right about there. Okay, 107, let's say, okay, for our critical frequency, which is what we calculated through this equation, right? Through this equation. You can cross-check that yourself. So that works out pretty nice, right? That has a really good correspondence to it. Okay, what's next? Well, how about the input network? Well, it's going to be the same sort of deal. This capacitor is going to drive a load impedance looking this way, and then, whatever's behind it. So we're going to have a source, RS, which is only 50 ohms. It's not going to have much impact. And then whatever the Z in over here happens to be, all right? And so I don't forget, like I did last time, let's change this back to 100 mics. And I'm going to do the same trick with this cap on the input. I'm going to change this to 100 nano. Now we just have to figure out what this impedance is. Well, you're going to have RB in parallel with Z in base. What's Z in base? Well, Z in base is beta times R prime E plus RE. Well, your RE is 100 ohms. Your R prime we already estimated to be about 13 ohms, right? So you've got 113 ohms times the beta. Well, what's the beta? For an 04, luck of the draw, 150, 125, 171.9. It's probably going to be somewhere in the mid-hundreds. So, let's just say it's 150, just so that we can get a ballparky kind of number. So if I take that and I say we've got, beta of 150 times 113, and now I'm going to put that in parallel with the 20K, right? That's going to give us, a little over 9K, like 9.2K. And then when you, again, use this formula, get your 9.2K, you're going to equate that with the X sub C and the R, And the capacitor value now is 100 nanofarads. We grind that out, and we get like 170 some odd hertz. But again, this is going to depend a little bit on what that beta is, because the Zn is going to be around the size of the RB. So, beta is going to have a little bit of an impact here. But in any case, let's go back up and we'll do another AC transfer characteristic. All right, so once again, here's the flat bit. All right, get a cursor out here. And I'll move them over here again. 28.8, so again, we're looking at like 25 and change. Okay, somewhere around there. I'm getting about 150 hertz. All right, so maybe that beta is, in fact, a little higher, than what we were expecting, or what we assumed, I should say. We can kind of play around with that, but that is good. It's telling us that, again, this capacitor is going to react against this resistance that we see looking in here. Moving right along. Okay. I mentioned at the outset that the bypass capacitor is not a true lead network. All right. What do I mean by that? Well, these lead networks roll off forever. In other words, if we look back over here, as the frequency gets lower and lower and lower, this thing just keeps getting bigger and bigger and bigger and bigger and bigger until finally, when you get down to DC, when you get down to 0 hertz, right, this thing is open and there's no signal getting to the load. That's not really what happens here. When you get to a really, really low frequency, this cap opens up, but the resistance can't be any lower, right? It can't be any bigger than whatever the RE biasing resistor is. You're limited to 4.5K. So we get a response that rolls off and then sort of flattens out. Instead of just rolling off forever, it kind of flattens out. So there's 2 frequencies of interest. How do we find those? Well, first off, before I forget, let me change our insanely large 10 milli over here. Okay, 10 milli. It's just such a huge value, 10,000 microfarads. So I'm going to bring that down to a simple microfarad capacitor. All right. Again, what does this thing drive? Or what is, on a Thevenin equivalent, what is driving this cap? Looking back in here, again, this DC power would be shorted. I'd see 4.5K in parallel with the impedance looking back this way. Well, that's the swapping resistor of 100 ohms, plus whatever we see looking into the emitter. Well, the first thing I see looking into the emitter is R prime E, so that's 13 ohms. And then, looking out this way, this is the current source. So that's a real high impedance. We can ignore that. And then looking back this way, we see RB in parallel with this stuff. The RS is only 50 ohms, so this total impedance is going to be really small. Plus, it's going to be divided by beta, because we're sitting out here in the emitter, and this is the base, right? This current is beta times smaller, so the effective, kind of like a transformer, right? The effective resistance that you see is chopped down by beta. Just like when we're in the base, whatever's out here in the emitter looks beta times bigger, like Z in base. When we look the other way, everything out here looks beta times smaller. So, this is going to be, this whole thing divided by beta is going to be a fraction of an ohm. And consequently, what we see is essentially the 100 and the R prime of 13. So, 113 ohms in parallel at 4.5K, which is about 113 ohms. All right. So when you grind through that calculation using 1 microfarad, you're going to get around 1400 hertz. Okay. And then we want to see where this thing sort of flattens out secondarily, which is essentially where the bypass capacitor winds up equaling RE, 4.5K. Again, we just exploit this formula, and you'll find that occurs somewhere around 35 hertz. And I really do suggest that you get out your calculator and you verify these computations yourself. Don't just trust me. In any case, let's go back to our analysis one more time. Alrighty. The usual. Hey, look! So here's our first break. It comes down like we saw before, and then it flattens out, unlike what we saw before. So let's get our cursor out here. Let's see what we got. So no big surprise. The flat part's 28.8 again. So where does this fall to 25.8? Somewhere around there. And that's 1.376K. So I approximated that as, like I said, 1400. So that's looking really good. The other one I said was going to be somewhere around 35. So to do that, what we want to do is find out what the gain is down here. That's minus 2.9 dB, right? Nearly minus 3, which would be the signal actually getting cut in half. Our amplifier is no longer amplifying. It's a de-amplifier. It's actually a very expensive attenuator at this point, way down here at 2 hertz. But in any case, so we're sitting down at minus 2.9. So I'm looking, actually, if I push it all the way down here, it's virtually minus 3. So I'm looking at 3 decibels above this point. All right, so minus 3, we go up 3. So I'm looking for about where it hits 0. And, here we are somewhere around, 34, 35 hertz, right in that region. So again, that's where the bypass capacitor winds up equaling RE, and the bypassing no longer exists. It doesn't bypass anymore. Okay? Beautiful. So we can see how we can come in here and determine what the critical frequencies would happen to be. But more useful, as a designer, you now know how you can set a lower frequency limit. You just sort of reverse the process. In other words, you got this formula, you just need the R and the C, right? In this case, you would know what you want your lower frequency to be. Oh, I want to be able to go down to 10 hertz, whatever the heck it is. And then you would know the R value, right? Out here, it's RC plus R load. Out here, it's basically the input impedance. Unless you have a really high source impedance, it's basically going to be the input impedance. Over on this guy, we're looking at the swapping resistor and the R prime E for the most part, unless you have a really high source impedance back here. But in any case, you know the R values. So you just manipulate this formula where C is the unknown, right? And FC is the known value, your target. So you just calculate what C has to be. You set the C to that value and off you go. The only thing I'll caution you is you wouldn't make all 3 of these critical at the same frequency, because what would end up happening is you'd get loss for each of them at the same frequency. So you'd actually have 3 separate losses, and you'd have a little bit more loss there than you would actually expect. If you really wanted to go down to 10 hertz, for example, you would make one of them critical at 10 hertz, maybe this one, because this usually has the biggest cap value. And then take the other 2 and push those down even lower, to maybe a couple of hertz or 1 hertz or something like that. All right, beautiful. So there we have it. You can analyze the lower frequency limit. And, one more thing in passing. You're going to see the same kind of configuration with other circuits. We have common collector emitter followers. It's going to work out kind of the same way. We're going to have FET amplifiers, junction FETs, JFETs. Similar kind of thing. You can use this same technique to find out what's happening at the low end on those as well. All right, we'll see you next time.